The advent of plate tectonics was like a veil being removed from in front of our eyes. It explained so much about the way the world was like it was. For example, the interaction of plates specifically at their boundaries accounts for the distribution of earthquakes, the location of mountain ranges along the edges and in the interior of continents, and for the distribution and types of volcano across the globe. In short, it deserves its title, the grand unifying theory of geology. It explained everything. Well, actually, not quite everything. There were some troublesome points. For example, although most volcanic and seismic activity occurred at plate boundaries, not all of it did. This was a wrinkle in the theory of everything geological, a wrinkle that can be summed up in a particularly beautiful series of islands in the Pacific, Hawaii. Hawaii didn't fit the existing model. It occurs in the middle of the Pacific plate, not at a plate boundary. And as we know, Hawaii is very volcanically active. How do we account for Hawaii? This was a question that geophysicist John Tuzo Wilson would try to answer. Professor Wilson would propose a workaround to explain the anomalies like Hawaii. He suggested that the islands were created as the northwesterly motion of the Pacific plate moved over a fixed hotspot in the Earth's mantle. As the plate moved over this hotspot, a new volcano was generated. This neatly explaining how the islands to the northwest of the big island of Hawaii get progressively older, smaller, and eroded as they are removed from the source of the new material over the hotspot. Through the pioneering work of Wilson and other researchers like geophysicist W.J. Morgan, we now have a working hypothesis of how these hotspots form, a hypothesis that involves deep earth structures called mantle plumes. Mantle plumes are thought to develop at the core mantle boundary, at around 1,800 miles deep. This was identified as the place where plumes might develop due to the dramatic change in temperature that occurs there. Temperatures in the core are around 2,000 degrees centigrade higher than the mantle. It is thought that there is little, if any, transfer of material between the core and the mantle, so heat across the interface must be transferred by conduction. Plumes are postulated to form in a layer called the D layer at the bottom of the mantle, as the rocks there heat up and become buoyant. It is important to note, though, that we are not generating magma. The pressures are probably too high to allow significant melting to occur. Instead, the rock of the mantle moves slowly over millions of years, like slow-flowing taffy. According to the plume hypothesis, this produces a cylindrical column of hot mantle rocks moving away from the core and towards the Earth's crust. As the plume moves up through the mantle, it starts to develop a bulbous head. This head is formed as material moves faster through the conduit than the head of the plume moves through the mantle. These differences in speed create the characteristic mushroom structure seen in plume modelling experiments. Eventually, the plume impacts the base of the crust, flattens out and spreads out for thousands of kilometres. At these higher levels, pressures are much less than at the core mantle boundary. This allows these hot rocks to undergo decompression melting and start to generate what is called a partial melt. In partial melting, only the minerals with the lower melting points will actually melt, producing a compositionally distinctive magma. When you partially melt mantle rocks, called peridotites, the magma you produce is basaltic in composition. Under this hypothesis, the Hawaiian Islands are the surface representation of a mantle plume that has been, and still is, impacting the base of the Pacific plate. The partial melting of the peridotite generates the basaltic magma that erupts as basalt lava, forming the Hawaiian chain. Interesting stuff, right? Yes, but also a little sobering, as it is possible that the development of just such a plume below Siberia would trigger a cascade of events that would bring all of life to its knees in the greatest extinction this planet has ever seen. So in this episode, let's ask, what was the world like before the hammer dropped? How did plumes trigger catastrophe? Was the Permian Earth turning into an acid nightmare? What role did microbes play in catastrophe? And consider the world that remained as a new era dawns. The Permian period was an interval that experienced a gradual warming as the continents came together to form Pangaea, the supercontinent that Alfred Wegener had proposed in the early 1900s as part of his hypothesis of continental drift. It was a world with oceans containing beautiful coral reefs, above which would swim numerous creatures like these nautiloids, relatives of squids and the modern nautilus. Other aquatic organisms included numerous groups of fish and sharks, like the bizarre Helicoprion with its buzzsaw teeth that has no modern dental analogue. On land, you would see plants colonising lowland areas. In northern Pangaea, there was a diverse flora of horsetails, ferns, cycads, a variety of major sceneferd lineages, and conifers, some of which had kind of a modern cast to them by now. By contrast, in southern Pangaea, the flora of the north was mostly absent. Instead, the flora was dominated by glossopterid seed ferns, such as Glossopteris with their mostly tongue-shaped leaves. In the later Permian, terrestrial vertebrates would diversify into a variety of forms, including archosaurs, ancestors of the dinosaurs, herbivorous reptiles like dicynodonts in a variety of forms, large predators like the gorgonopsians, and cynodonts, who would evolve into the Triassic and were ancestral to the first true mammals. And all of this beautiful world collapses, fundamentally, almost totally. This is not just a pruning of the tree of life. The tree of life would be reduced to a few wandering branches, a poor shadow of its former self. By the end of the Permian, it is possible that up to 95% of species have been driven into extinction in life's greatest crisis in the last 540 million years. Paleontologist Dr. Doug Irwin in the Department of Paleobiology at the Smithsonian's National Museum of Natural History has long wrestled with this most catastrophic event in life's history. Doug visited my current hometown, Vancouver, for a conference in 2014 that was hosted by the Geological Society of America. He was one of many fascinating presenters at a session entitled Mass Extinctions, Volcanism, Impacts and Catastrophic Environmental Changes. One of the many insights he provided, this one stuck in my mind as it really brings home to me the extent of the event. The end Permian saw the sweeping away of many of the main players of what we could call an old Paleozoic world, a world full of trilobites, corals and brachiopods. As Doug put it, the composition of a tidal pool today is a reflection of who lost and who won during this event 252.4 million years ago. In short, the Permian extinction has fundamentally shaped the biosphere we live in today. Actually, we now think that two plumes could potentially be involved in this event, causing two and not one extinction event. The first occurred around 260 million years ago, about 8 million years before the second, more catastrophic event at the end of the Permian. This first so-called Guadalupian extinction occurred in both marine and terrestrial environments. Marine extinctions were varied among locations and the types of taxa impacted. Brachiopods and corals record severe losses, as did important groups of microfossils like the fusillinid foraminifera. Recent research in the Karoo region of South Africa, led by Michael Day of the University of Witwatersrand in Johannesburg, and including Doug Irwin of the Department of Paleobiology, has shown that around 74 to 80% of terrestrial species becomes extinct. This includes the impressive Dinocephalia, a group of large, heavily built therapsid mammal-like reptiles, the most famous of which probably is the most wonderfully named moss chops, a herbivore around 9 feet long. The plume event, thought to be related to this extinction, occurs in China and produces a volcanic outpouring called the Emishan Traps. This volcanic event is dwarfed, though, by the next plume to ascend from the depths. This would develop under Siberia at the end of the Permian, generating volcanism known as the Siberian Traps. The Siberian Traps volcanic deposits cover over 2 million square kilometres today, an area comparable to that covered by Western Europe. The original coverage at the end of the Permian was about 7 million square kilometres. Due to its scale, the Permian extinction rightfully receives a lot of research attention. As a result, our understanding of this event changes rapidly. One of the recent updates regards the timing of Siberian Traps volcanic activity. It is still known to be coincident with the extinction event, but it would appear that the duration of the event was shorter and sharper than previously thought. Research at the Massachusetts Institute of Technology by Sam Bowring and Richard Schrock suggests that the traps activity was around 10 times faster than previously thought, taking place in just 60,000 years. That is an instant in geological time. As we have mentioned in earlier lectures, it is not the vast amounts of lava that would be the most significant problem during these events. Creatures could easily migrate out of the affected area. Rather, the greatest problem are the gases that it produces. Research at the Carnegie Institute of Washington by Benjamin Black and Elkins Tanton investigated inclusions of gas trapped in the lava from the Siberian basalts. In effect, these melt inclusions provide a sample of the gases that were actually being produced during the event. The Carnegie research team had a particular interest in the amount of sulfur, chlorine and fluorine gases that were being produced. From this, they estimated that between 6,300 and 7,800 gigatons of sulfur, 3,400 to 8,700 gigatons of chlorine, and 7,100 to 13,700 gigatons of fluorine were released to the atmosphere. A gigaton is equal to 1 billion tons. If these gases reach the upper atmosphere, they could cause significant environmental impact. Add to this the vast amounts of carbon dioxide also produced, and the traps volcanisms have produced a deadly cocktail. Both sulfur dioxide and carbon dioxide can be dissolved in rainwater, forming highly acidic rain that could impact plants and soils on land. Some think that the acid rain fell from the skies with a pH of around about 2, close to the acidity of undiluted lemon juice. This could have been falling in the northern hemisphere at this time. The pH of rain would likely return to normal levels after each volcanic episode, but the regularity of these events would have meant that a regular occurrence of acidic lemon juice from the skies would have occurred. The pulsing activity of the volcanic traps would also inject chlorine and fluorine into the atmosphere. These halogen gases are known to have serious impacts on the ozone layer. Ben Black at MIT has estimated that ozone levels could have decreased by a conservative 5% to an extreme 65%, particularly at the poles. Such ozone depletion would expose animals on land and in shallow levels in the oceans to dangerous levels of ultraviolet radiation. But perhaps an even more significant product of the traps was the vast amounts of greenhouse gas, carbon dioxide, that was produced. The problem was compounded by the rocks that the traps were erupted through, rocks rich in calcium carbonate, limestones. When you heat limestones, you guessed it, you produce lots of carbon dioxide. There were other rocks causing problems too, as there were also significant deposits of coal in the same area. As the hot magma and lava combusted the coal, it generated even more carbon dioxide and additional toxic gases. Even if not combusted, the heating of coal could also produce significant quantities of methane, another important greenhouse gas. A rise in carbon dioxide would have inevitably led to a rise in global temperatures due to the greenhouse effect. It is thought that this would have helped to destabilize certain gas-rich deposits in the oceans. These deposits form in offshore continental margins where it is cold even in tropical areas. The cold temperatures and high pressures cause ice to complex with microbially generated methane, forming what is called a methane or gas clathrate. Now, clathrates are very sensitive to temperature changes. It's proposed that the traps induce warming raised ocean temperatures to the point where the clathrates started to destabilise and release their methane. Methane is an even more effective greenhouse gas than carbon dioxide, and although methane oxidises quite readily in the atmosphere, what it produces when it does is even more carbon dioxide. Today, there is enough methane in clathrates to total twice the amount of carbon to be found in all known fossil fuels on Earth. There were probably plenty of clathrates in the Permian too, so not only do we have an initial global warming from the traps produced carbon dioxide, but gas clathrates may have also contributed to the situation, perhaps rising global temperatures by the end of the Permian by as much as 10 degrees centigrade. You can see methane bubbling out of muddy sediments on the seafloor today. Can you imagine vast clouds of methane that might have been released from the Permian oceans? In Doug Irwin's excellent book Extinction, he calls the chapter dealing with causes of extinction a cacophony of causes, a very appropriate title. And apart from the Siberian traps, Doug lists a whole bunch of tipping mechanisms that have been proposed as possible causes of the end Permian crisis. Everything from drifting continents, rises and falls of sea levels, cosmic radiation, impacts from space, and my personal favourite, interaction of our planet with dark matter. It would appear, though, that at the moment the most likely triggers are the Siberian traps and the consequences they would have on global climate. But what were the killing mechanisms? On land, we have a signal that suggests the collapse of the flora, a signal that is recorded in the style of the river systems transitioning from meandering plant-stabilised to the more disorganised braided systems, suggesting a sudden decimation of plants on land. This collapse of land flora may also explain the lack of coal in the early Triassic, the so-called coal gap. And why do we see this collapse? Here are some ideas. First, the Siberian traps were likely a dirty eruption. The coal we mentioned, ignited by magma, would burn and produce a lot of fine particulate material that could have blocked sunlight. In addition, sulfate aerosols produced by the eruption may have also contributed to global dimming. As the sky started to dim behind the haze, photosynthesis started to diminish. Even after the ash was washed from the skies, the carbon dioxide and sulfate aerosols would likely fall as acid rain and poison the soils. Probably more significantly, though, would be the carbon dioxide that would initiate global warming and drive the already dry Permian world into drought. Plants and the rest of the terrestrial life that they supported collapsed catastrophically. But what of the oceans? It's been suggested by some that extinction in the oceans lagged somewhat behind the initial extinction on land. The reason for this is that water bodies act as temperature buffers and respond more slowly. More recent evidence, though, suggests that extinction was more or less simultaneous in both realms. Whenever it hit, the catastrophe was probably even greater in the marine realm. What happened here? Firstly, the oceans became slow and sluggish as a warm layer capped the oceans and reduced vertical mixing and circulation. This means the ocean's ability to circulate oxygen from the atmosphere to the ocean was seriously impacted. Microplankton would still have thrived in the warm, oxygen-rich surface waters. When they died and sank, though, they decayed and used up those dwindling oxygen supplies in the deeper water, driving the oceans into a state we call anoxia. It's been suggested that an even more significant effect than decreasing oxygen levels, though, was an increase in carbon dioxide. Carbon dioxide is more soluble in water than oxygen, and thanks to the Siberian traps, there was a lot of extra carbon dioxide in the atmosphere that was starting to dissolve in the Permian oceans. Elevated carbon dioxide in the oceans may have led to elevated levels of carbon dioxide in the bloodstreams of marine-dwelling organisms, a condition known as hypercapnia. Terrestrial organisms are actually better adapted to cope with increased levels of carbon dioxide in their blood when compared to marine organisms. For us landlubbers, carbon dioxide is removed relatively slowly from our bodies. We have to use complex organs like our lungs to facilitate gas exchange. As a result, carbon dioxide tends to hang around in our bodies longer than for marine creatures. This is why we have evolved a higher tolerance for elevated levels of CO2. In aquatic species, carbon dioxide is more easily flushed from the body. Gas exchange is a much simpler process in an aquatic environment. This means that even moderate levels of hypercapnia in poorly carbon dioxide adapted marine species could cause various metabolic problems such as reduced protein production and decreased fertility rates. But there would be another consequence of increased levels of carbon dioxide, for as carbon dioxide dissolved in the oceans, they started to become more acidic. This development of acidic oceans matches the patterns of organisms that were hit hardest during the extinction. Creatures that secrete calcium carbonate shells, brachiopods, echinoderms and corals were severely affected. This is especially significant when considering that corals and the organisms that lived on, in and around them constituted an entire complex reef ecosystem that would all collapse as well. A team led by Dr. Matthew Clarkson of the University of Edinburgh in Scotland has been studying this phenomenon by analysing carbonate rocks in the United Arab Emirates. At the time of the extinction, the UAE lay in a huge embayment encircled by the eastern edge of Pangaea called the Tethys Ocean. They studied changes in the ratio of boron isotopes that are known to vary with pH. Their analysis suggests a decrease of around 0.6 to 0.7 pH units during the extinction. Now, this might not sound like much, but that represents a catastrophic change for ocean chemistry. The boron acidity signal occurs about 50,000 years after the extinction event. They propose that the Permian-Triassic extinction was a two-phase event. The first pulse, over 50,000 years, was fairly slow as carbon dioxide was added incrementally to the Earth's oceans and atmosphere by the Siberian traps. It is possible that the oceans, which are pretty alkaline, were able to buffer the carbon dioxide being dissolved in the sea water until a critical point was reached, when a second pulse of CO2 was released over a period of about 10,000 years. They suggest that this pulse released about 24,000 gigatons of CO2 at a rate of about 2.4 gigatons per year. Such a massive flush of carbon dioxide into the Earth system would have overcome the buffering potential of the oceans. Seawater would be driven into an acidic range and the reef ecosystems crashed. We have already described how acid rain on land would likely have caused problems for the terrestrial ecosystem. Evidence for this, though, has not been all that forthcoming, although most agree that it is likely to have occurred. However, a team of scientists, including Mark Sefton of Imperial College in London, have found some intriguing evidence that might act as a proxy for the acidification of soils on land. To explain what that proxy is, we need to look at what the acid rain does to soils. Acid rain increases the solubility of plant-toxic metal ions like aluminum. It will also leach calcium and magnesium and other nutrients from the soil profile. In this way, acidity in soil causes problems for root systems in their development and in their ability to take up nutrients, causing the plants above ground to wither and die. Acid rain percolating into the soil profile would also seriously impact vital microbial and fungal diversity that occurs in soils. Microbes in particular show very low diversity in acidic soil conditions, and fungi don't thrive too well in pHs lower than 4.5. Fungi and bacteria in healthy soils help in the breakdown of complex plant molecules like cellulose and lignins, that's wood and bark, and animal chitins, exoskeletons and so on, as well as fungal molecules into simpler organic molecules that can be used by other life forms. This breakdown is facilitated by enzymes that fungi, bacteria and other microorganisms secrete into the soil. With elevated levels of acidity, these enzymes are severely inhibited or destroyed. An important step in this enzymatic decomposition of lignin is the production of a substance called vanillin. Vanillin undergoes further enzymatic alteration and is oxidized to vanillic acid. This part of the process, though, is very pH sensitive, with optimal chemical change at about a pH greater than 5. As such, the relative proportions of vanillin to vanillic acid may give us an idea of the degree of soil acidity. Finding old soils, or paleosoils, is difficult though, especially as it is likely that much plant material in soils was eroded and washed away from the fossil record. Fortunately, this soil washout can be picked up in marine sediments by the presence of things like filaments of soil fungi and also a common organic component of soil profiles called polycyclic aromatic hydrocarbons. The team investigated a section in the southern Alps of northern Italy that contained evidence of these soil washout markers and analysed the ratio of vanillic acid to vanillin. What they found was a pattern that pointed towards a series of pulses of acidity on land. The team suggested that these pulses were related to individual episodes of volcanic activity from the Siberian traps and associated acid rain events. This is still pretty new research and there are a lot of wrinkles that need to be sorted out, but this study could be some of the first concrete evidence that we have of an acid planet both in the oceans and on land during the Permo-Triassic transition. It is possible that microbes may have played an important role in the Permian extinction too. The microbial world is often overlooked though. It's not showy, it doesn't work well in simulations in TV. A reconstruction of an ancient microbe floating in an ocean doesn't really have the same appeal as a Tyrannosaurus rex hunting down a Triceratops. Nevertheless, microbes are a fundamental part of the biosphere. Their presence can both be essential and catastrophic to the health of the biosphere. Given that they can reproduce and spread very rapidly, they can respond very rapidly to environmental changes and opportunities, as may be the case for the microbial life at the end of the Permian. In a recent paper, a team including MIT researchers Daniel Rothman and Gregory Fournier suggest a potential source of methane in addition to the clathrate methane we described earlier. This methane, they suggest, may have come from a microbe called Methanosarcina that belongs to an ancient group of microbes belonging to the Archaea. Their research into the genome of this microbe points to a change that occurred at about the time of the Permo-Triassic extinction. This change would have permitted Methanosarcina to produce significant quantities of methane and, as a consequence, more global warming. In this scenario, the Siberian traps still act as the trigger, or more accurately, a fertilizer. One of the elements that the traps would release into the environment is nickel. Nickel is a vital fertilizing element for these particular microbes and would have permitted their rapid blooming and the production of large quantities of methane. There is another type of microbe that would likely have serious impacts on the biosphere as well. As we've already discussed, the Permian oceans were becoming oxygen depleted, anoxic. Certain microbes have a preference for living in such anoxic conditions and gain energy from stripping oxygen off sulfate molecules. In doing so, these sulfate-reducing bacteria produce a dangerous byproduct, hydrogen sulfide. Hydrogen sulfide is highly toxic to the metabolism of most organisms and would have a serious impact upon ocean ecosystems. This is not mere conjecture though, as biomarkers of sulfate-reducing bacteria have been found in Chinese sections that cover the Permo-Triassic boundary. Significantly, these sections were originally deposited under shallow water conditions. The placement of these deposits indicate that oxygen-poor, hydrogen sulfide-rich water encroach and extended from deep ocean water well into the shallow, well-lit areas of the oceans, just where those Permian coral reefs grew. It would appear that during the late Permian, in addition to increasing temperatures, increasing oceanic acidity, and reduced oxygen levels, the Permian reef systems were being poisoned too. What was left was a decimated world, baking in a hot sun with slow, sluggish, poisoned oceans. The Permian extinction provides an insight into a biosphere which has ceased to function. There wasn't any single cause why the extinction occurred, even though there might have been an initial trigger in the plume that rose from the core and impacted the base of the lithosphere in Siberia. It is becoming increasingly obvious that the only way to understand our world is by considering it as a system composed of interacting parts. Although we like to partition the world up into convenient packets like geology, climatology, oceanography, and even economy, in trying to understand any of these human-defined divisions of reality, we cannot truly understand them if we view them as individual standalone disciplines. A simplistic, discipline-driven view of the world will obviously be limited and miss the bigger picture. Even more significantly, a failure to appreciate that the impacts on one system will generate impacts in other systems is also very dangerous. The Permian extinction was not a simple cause and effect paradigm like dominoes falling in a row. In dealing with a complex interacting system like the Earth, a catastrophic event like the Permo-Triassic extinction has to be viewed as a cascade of events that rapidly spread and expanded till it impacted almost every corner and level of the Permian biosphere. It often takes hundreds of thousands of years for the biosphere to start to recover from such events, but things would be different for the Permo-Triassic extinction, as 5 million years into the Triassic, the Earth was still a pretty devastated planet. We will investigate why in the next episode.